In probability, the Poisson distribution is a pretty useful tool or formula, however you want to look at it, that essentially tells us that given a fixed time, we can find the number of events that can occur, or the probability of it rather. So just looking at the formula we have here, we can see that the probability of x equal k, where x is some random variable, right? Which is the number of events, and then k is the um, number of events we're observing. So given the question or circumstance, this will always change, is equal to this symbol over k times e to the minus symbol. What does this all mean? Well, our symbol here is called lambda. It is another way of essentially saying the mean, or mu, right? Whatever you want to use. Or you may know it as the expected value, right? Expected number of trials. E is obviously Euler's number, and k to the factorial is the same k I mentioned before that we're dealing with. And now, looking at this formula and knowing it, where does this come from? Well, let me explain. Because I always believe it's rather important to know where formulas come from to sort of get some intuition on how to use it as well. So, knowing probability, the probability of a random variable equaling k is the amount of combinations, so n choose k, or rather the limit of n approaching infinity, because we're not given like a fixed amount of trials, right, or a fixed amount of objects, so n choose k times the number of successes, right, so our average divided by k, or divided by n, over the amount of successes, which is our n that we're, or our k that we're observing, right? And then all this times the number of failures, because failures have to happen. And if that's 0, then so be it. And so our number of failures is obviously 1 minus the probability of success times all the, or to the power of how many times our test didn't succeed. So n minus k, right? And we could rewrite this as developing our n choose k here and moving some of the exponents around and such. So we get n factorial over k factorial times n minus k factorial times lambda to the k, n to the k, times that whole spiel. And now, just looking at this at first, how do we go from here to here? There's nothing to really simplify at the moment. There's nothing much we can do, so how do we get there? Well, it's best to look at each factor individually and see their limit of an approaching infinity. That's just a good uh, lesson or trick in general. So let's look at our first term, our n choose k. Well, a cool trick if you'd want to call it, is approaching infinity n factorial over just n minus k factorial is around n to the k, right? Such that this just becomes our k factorial is still there, so we can rewrite this as n to the k over k factorial times what we have here. We're not going to change for the moment. Times this. Now let's see how we can develop this to fit our needs. So another cool trick is that the limit approaching infinity of, let's use some example x instead, of 1 plus a over x, all this to the x, let's say is equal to some limit point L, some arbitrary limit point. Well, if we develop this and take the natural logarithm of both sides, we get that approaching infinity, x times the natural logarithm of 1 plus a over x is equal to the natural logarithm of our arbitrary limit point. And now if you know anything about Taylor series, approaching infinity, as the series develops, this essentially in simple terms just becomes a over x, because all the higher order terms essentially negate. So this really just becomes x times a over x is our natural logarithm we have over here. So obviously we can evaluate to see that a is equal to the natural logarithm of L. Taking e to the both sides, then e to the a is the natural logarithm of L. And say that a is equal to minus lambda in this case. Well, this becomes a minus, right? And that's what it looks like our term over here. And we could rewrite what we have here as e to the minus lambda. And so developing more on our findings, you could probably already see that we can simplify our n to the k. So we could simplify this. And we can already write this as something pretty familiar. So actually, in fact, because we already evaluated each of the factors to the limit, we can actually remove this, and we weren't really supposed to have it in the first place. So this just becomes what we're left with. So our lambda to the k divided by k factorial times our e to the minus lambda, which is exactly the Poisson distribution. So that's how we got the formula, and that's sort of the intuition behind it. But now, how do we use it? So thinking back to what I said at the start, when you think of the Poisson distribution, think fixed time and number of events. And so when you're problem solving, you can sort of remember to look at these factors and apply this formula to it, and I'll show you how. Oh, sort of erased a little of our notes there. And now I do have a question in the clipboard. Let's make that black actually. Or, yeah, black with a white background. Alright, so neatening this up. Our question states that. Alright, so neatening this up, our question states that a call center receives on average 5 calls per hour. Okay, assume the number of calls follows a Poisson distribution. What is the probability that the call center receives exactly 3 calls in an hour? So 5 calls per hour sort of should scream out to average, right, or mean. So our lambda, given the formula, is 5. And 3 calls in an hour. Well, if we're looking at the probability that exactly 3 calls per hour occurs, well, that's our k. It's the number of events we're observing. And now we're looking at the formula. We have all the variables we need already, just given those 2 inputs. So the probability that x equals exactly 3 calls an hour, where x is the number of calls in an hour, right? Is equal to our formula given our inputs. So 5 to the lambda over, or to the k, which is our 3, times e to the minus 5 over 3 factorial. And writing this out, we get, I know 5 to the power of 3 is, I believe, 120. And e to the minus 5 I'll evaluate after. But we know that 3 factorial is 6, which is, let's just write 20 to the e times e to the 5 for now, which is around 0.1347. So let's say around 13.5%. So that's the probability that the call center will receive exactly 3 calls in an hour. 13.5%. Roughly, right? Now for our second question. What is the probability that it receives at most 2 calls in an hour? Now what does this mean? The probability that x, or number of calls, is at most, so below or equal to 2. Now we don't really have any probabilities that show an exact number, so we can't really apply the Poisson distribution yet. However, given what we have, we can rewrite this into a measure of probability using x equals something exactly. And so at most 2 given the sum law, is really just the probability of x equaling 1 or x equaling 2. So the probability that x equals exactly 1, so they get 1 call per hour, or they get 2. And now we can easily apply the Poisson distribution. So in our uh, first probability here, our k is 1 and our k is 2. And the average call doesn't change, it's still our 5. So lambda is 5. And so the probability that x is below 2 is we'll have to write the distribution formula out twice, right? Which is our 5 to our first k times e to the minus 5. That'll stay the same for both formulas, and e to the 1, which we can just write as 1, plus 5 to the, sorry, I wrote this as 3, 2, 5 to the 2 times e to the minus 5 over 2 factorial, which is just 2. I don't like to write the factorial, which is just 5 times 5 plus 25 times e to the minus 5, which if we calculate this, just to make it easier for myself, I'm going to write down the result of each, though. So 0.0336 plus, or we could just do 5 times that, so 0.168, which as a whole becomes around 0.2 or 20%. So the probability that they receive at most 2 calls an hour is 20%. And so when you're solving for problems, the key takeaway here is look for the fixed time, right? So the probability that, something will occur exactly something amount in an hour, right? An hour per hour, right? Right? We're seeing sort of pattern, and the number of events. See in the question, it's asking, at most 2, exactly 3. And usually the hard part about using the Poisson distribution is just rewriting the question in a way to apply it like we did here. Right? Immediately we can't apply the formula, but writing it out as the sum of 2 exact probabilities, then we can. And for some questions too, the time scale changes. So maybe this says per hour, but these say per day, and you'll have to solve for a different lambda or a different mean. So depending on the question, always have some intuition. That's sort of why I like to explain the formula first, and I hope that helped you.